All right, well, we might as well go ahead and get started. Can you guys see my inventor screen?
No, I can't.
See a blank screen.
See a blank screen, all right.
So it's not your, yeah, all I see is black
Okay.
with your fire pointer, and that's it. There you go.
All right, we got it up now. Good. At least we didn't get too far with the black screen. So what we said last time is that we've taken a look at AutoCAD and we've taken a look at all the assignments and selected some to show kind of the depth and the breadth that we go through to satisfy the tag requirement. And but we talked about that the world of parametrics is probably more relevant to you, and thought we'd go through some of the labs that we do here at Columbus State in the world of parametrics and a little bit behind them, so that kind of have a flavor for that. Does that sound agreeable to everybody?
Yeah, that's fine with me.
Okay. So just to kind of review here real quick, we do 10 labs. Oh, that's not the one I wanted. Here we go. Let me get up here to the top. So we do 10 labs in the parametric class to kind of get everybody just warmed up to the world of parametrics and constraints and creating detailed drawings and kind of all the things that go with that before we start any projects. Our real goal is to start projects in the class, kind of start out in assemblies after these 10 labs, and then move into sheet metal, and then do a project in inventor sheet metal. And from there, they'll kind of reverse engineer something. It's always interesting because if we reverse engineer, have a little tapping machine or pliers or what have you, it's the manufactured parts are way more complicated than the labs that I've asked them to do. So there's a challenge there. And then we try and get into the actual designing of things that don't exist, where I don't know the answer and they really don't know the answer, and we kind of go down that road together, because that's where the world of parametrics was really designed for, or intended for, was to design things. So just reproducing things only gets you so far. And so this is the first lab that we do. This would be the second. The third, you can see they're pretty simple. This is the fourth lab, a little bit more complication. This is the fifth one. This is the first lab that actually requires additional sketches. The first four they can accomplish with one sketch, extrude it, and the part's done. So now they have to do some additional altercations to the model to complete the part. Same thing with this one. Great use of constraints here on this one. So this one has a cylinder here at 45 degrees. That kind of brings us into planes, or forces us to use planes and introduce that topic. And I think we talked about this before. This one just has drastic height changes. Has quite a bit going on. Lots of different detailed drawings on here. And so the drastic height changes in the detailed drawings is what we're looking at. Lab number 9 here. Again, just trying to get more proficient with the software and use it to its advantages. I find that to be a big problem in the world of parametrics. Everybody's just interested in getting it done. And once they have it done, they can kind of check that off that they've completed it, but it's really how you completed it. So I warn everybody, these first 10 labs, I'm just trying to prepare you for the projects that are coming. So we got to get good at the world of parametrics so that when the situations become difficult, that we can use the advantages that the software offers. And so this is the last lab that we do in just the single part, and it doesn't really go to anything. So I thought we'd just go over a couple of these, selected some. Thought I would start with, let's see, this one right here, lab number 2. Pretty simple rectangle with a cylinder, half a cylinder in it, but offers some unique constraints, or at least the beginning of the application of constraints. So I'm going to start off with just a standard IPT. If you're not familiar with Inventor, same as all parametric softwares, it breaks the different files or different aspects of a drawing into different files. So we have a model file, and then we'll have another file for the detailed drawings, and then we'll have another file for the assembly, and we'll have a different file for the exploded assembly, and things of that nature. So I'm just going to start off here in Inventor, and I'm going to create a 2D sketch, and I'll just pick my XY plane to start that with. And for those of you that aren't familiar with Inventor, Inventor I think has for me, one of the better user interfaces. It's probably what I'm used to. I usually tell people it comes down to a Coke-Pepsi kind of argument. Some people prefer Coke, some people prefer Pepsi, but really they're both the same thing. So Inventor, SolidWorks, Solid Edge, they're all pretty much the same. It's not till you get to Pro Engineer or CATIA that you really see any different capabilities or really differences in the software. So one of the things is Inventor pushes the toolbars or the tool ribbons up here that you need at the time you need them. So as soon as I picked 2D sketching, it took me to this 2D sketching toolbar. It also offers me a command wheel. So if I just simply right-click my mouse, it brings up the most likely commands I need at this point. So if I wanted to create a circle, it's right here. If I wanted to create a line, it's right there. A two-point rectangle, it's here. Those same commands are up here in the ribbon, but I just end up not having to move my mouse nearly as much. The other thing Inventor's done is once you're used to this command wheel that comes up, you can do mouse gesturing. So I know that in this command wheel, my line command is always directly up. So if I get rid of my command wheel, if I just simply right-click my mouse and drag it, I get the line command, what would have been directly up. Escape out of that. I believe the circle was kind of up here to the upper left here a little bit. So if I right-click my mouse and just flick it really quick, I get my circle command so that I could draw a circle in here without having to actually take the time to right-click and pick what I want. So lots of different ways I could approach this, and I ask them to approach it a very specific way because I'm trying to really get them used to sketching individual pieces of geometry and getting used to the constraints. So one way that we could accomplish this task in Inventor is to simply just put a rectangle in here and then latch a circle. I'll just latch it onto the midpoint there. And that would be a perfectly acceptable sketch for that part. And I could start dimensioning this. My circle's already in the middle because I latched it to the midpoint here. So I start applying some dimensions. I'm not going to take the time to do that. And then I could extrude the shape that I want and get this kind of half moon shape in there. So for sure, that's an easy way to do it. I'm going to undo that. But the goal of this lab is to really start getting them thinking about the individual pieces of geometry. So I ask them to do it in that fashion. Grab that line command again. And get the geometry up there, and then I want an arc for this actually, so on my command wheel. So I'm going to put an arc in here. I'll start getting that. Now we have the opportunity to really start talking about constraints and getting students to use as few dimensions as possible and as many constraints as possible, because this is what's going to make the complicated parts easier. So for this one, first thing I would do is probably the collinear constraint, and I would get this line up here in line with that one. Probably go to my equal constraint and make this line equal to that one in length. And then possibly I could use my coincident constraint here. I could grab the center of that arc and make it coincident to that line. That's starting to look pretty good. So now we should be able to add some dimensions, and actually down here in the lower right hand corner, Inventor's telling me that I need 3 dimensions to finish that part. So I'm going to go ahead and apply those. That should actually be 6 inches in length. Zoom back out here a little bit. And my height that should be 3 inches high. And then my circle, or my arc here, that should be a 2-inch radius. So, zoom out here a little bit. So my sketch is turned purple, means it's fully constrained. And I can also turn on my constraints if I want to see those. I can show all degrees of freedom, which there were not any, and then here we go. So if I turn on my constraints, I can see symbols for them. I have my equal length constraint up here, and it highlights the geometry that that equal constraint is applied to, and here's my collinear constraint. You can see that when I was sketching this, because I sketched things really close to horizontal and vertical, those constraints were automatically applied. Here's a horizontal constraint. Here's a vertical constraint. Perpendicular constraint was applied to this one. I can set my preferences in the settings on what constraints I wanted to primarily look for as I'm sketching. But that's how I would approach this one, and then we would just simply finish that, and I would have them extrude this. My computer's a little slow here, so it's automatically found the only possibility there, and that was 5 inches long. So that's how we kind of handle that first lab, and I'm going to kind of go over all the different zooming functions. So we're going to talk about orbit. We're going to talk about changing the center point of our orbit so we can orbit around a specific point in the geometry. And the cube up here so that we can look at it conveniently from different angles or our isometric views, what have you. Okay. So that would be the first lab. I'm not going to bore you with all of them for sure here. So the next one that I think I'll demonstrate here is this lab, our lab number 4. So again, this is, I'm going to require them to do one sketch that does the outline of this part, and then constrain that sketch, dimension it, and extrude it. So start a new solid model here. Start my 2D sketch. I think I'll start with line command, so I'll just use the command wheel for that, and I'll start to drag this out here a little bit. When people are coming from the world of AutoCAD into this class, first thing they want to do is kind of go back to those old habits where if I drag this out, I have a heads-up display. I can type in the distance I want that line, and that's not necessarily a bad thing, but I think it works a lot better if we just get the sketch up there of about appropriate size with all the elements of the geometry that we need, and then we go through and do the constraints and then the dimensions. Because if I type this dimension in, which should be 5.4375, now I automatically have a dimension applied for that. And I've eliminated any possibility that I could have satisfied that with a constraint. So I'll go ahead and leave that one up there for now. But let me get the rest of these. Let's get an arc in there. Go back to my line command. Need another line in there. Need another arc. Grab my line command. Just trying to get the elements in here that I'm going to need. I'm going to need an arc. Okay, so from here, we're going to start applying constraints, and I'm going to grab my tangent constraint first, and, oops, didn't get that in there. Get my arcs tangent to my lines. So my tangents. I did notice that this line right here, I was a little sloppy when I sketched that, so it did not get the vertical constraint automatically. I'll go ahead and get that applied there. And then down here I can do a couple of different things. I could set this line collinear to this line, and that would bring them in line with one another. I could also set this line equal to that line. Doesn't really matter. Going to get the same result either way. And then I'm going to go ahead and take care of this arc. The center point of this arc really needs to be on the projected intersection of those two lines. So I'd need a true quarter of that arc right there. So I'm going to use my coincident constraint or my coincident constraint and tell it that that center point should be coincident to that line, and it should be coincident to that line. And now I have a sketch that can adjust in size and still hold together, and I maintain the shape that I was looking for. And that's the main reason that I ask them to always think constraints first and dimensions second, because it's when you have to go back and edit a part that you start to realize all those dimensions, if you dimension everything, really just become a giant pain. And the constraints are really there, I mean, they're there because they're parametric, and it's a great way to produce geometry, but you get to describe to the software the design intent of this part, so that we don't know what this part does, but if this line, if this surface, what will become a surface, has to always be the same as this surface, that it has to do with the function of this part, then I need to make sure I build that in with constraints, so that no matter how somebody else edits this, that I will always maintain that design intent. So I'm going to go ahead and start applying some dimensions here. That should be 2 inches. That should be 1.5 inches. I believe the distance there is 3/4 of an inch. 2.875 for that one. This one to the center of that arc should be 1.25 inches. And then my overall from the center point of that arc to the center point of that arc, that should be 5. And this is a good example that as I start to apply these dimensions, I've kind of lost a little bit of my integrity here. The sketch still has good integrity, but it's not the exact shape I wanted. So everybody starts to freak out at this point that they need to start over, but you're just not done dimensioning this yet. So you got to get everything in there. That you need kind of as you're going along here. So that's how we handle this one. Still have a dimension hanging out there, but that's fine. I believe it's just the radius of that circle. And I'm going to undo that. There we go. So if I turn on show my degrees of freedom, it shows me what's allowed to move. So without that radius dimension in there, that all of this geometry is allowed to move in the direction shown. So sometimes that helps me identify what's missing and what flexibility I have. So put that dimension back in there. There we go. So you would just finish this, extrude it out, zoom back out here, give it a distance. Part should be 2.25 inches, and there we have a finished part. So feel free to stop me anytime you have questions, otherwise I'm just going to forge ahead here. The next one I thought we would talk about is this lab number 6. And I call this one the key because it kind of looks like a key to me. But this allows us some nice opportunities to look at more applications of constraints. And this one would not obviously be a single sketch. We're going to have to do multiple sketches and add to it as we go. So I'll move that over there for now. So start my sketch here. I'll start off with just a circle. This is going to be the biggest circle on this thing, which is 2 inches in diameter. So that one was real simple. I just locked it down to the origin point, and I knew it was only going to take 1 dimension, no opportunities to create any constraints there. So we're going to finish that one. Then we're going to extrude that, and we're going to extrude that 0.875 there. So I'm going to select this surface. I'm going to start a new sketch. Again, I kind of have my commands follow my mouse. I could come up here and select 2D sketch, or it's just right here as a symbol, so I don't have to move my mouse nearly as much. And I need a circle that's concentric. And although I don't walk them through this, I do do it once for them up on the projector and kind of talk about why we do some of the things that we do. But I'd certainly tell them that they could start that circle kind of off to the side somewhere and then just force it to be concentric, because it really does need to be concentric. And I'd also show them that they can just simply latch it down to the origin. Since my first one was latched down to the origin, the second one can be latched down to the origin. And that has a diameter of 1.75. We'll go ahead and finish that. And we'll extrude it. And that extrusion should be 1 inch. So now at this point, there's some flats that exist on this. I'm going to bring the PDF back just for a second. So what I like about this one so much is these flats on the side. They're on both sides, as you can see in the side view. And those flats extrude back not only through this cylinder, but they touch on this cylinder as well. So I asked them to create those in kind of a very specific way. So I asked them to use rectangles as what we're going to extrude to actually cut. And I should be able to get these rectangles positioned correctly and only have 1 dimension on here. So this is kind of the design intent of my object. So the first thing I'm going to do is come up here to my coincident constraint, and I'm going to tell it that I want the corner point of this rectangle to be coincident to the larger circle. I'm going to do that for all of these inner points on my rectangle, on both of them there. And then I'm going to grab my tangent constraint, and I'm going to tell it I want this line to be tangent to the larger circle. Then I'll use my equal constraint, and I'm going to make these two equal. So now they can grow together. So if I adjust one, I adjust the other, and they're always big enough to cut out the shape that I want to create those flats. Because as we do design changes and dimensions changes, if I would have just put 2 big rectangles up there with a bunch of dimensions, can't guarantee that they're always going to be the right size to make the cut that I want. So I'm just going to apply a dimension. I have the distance between those 2 flats, and that should be 1.375. And then I'm fully constrained. So I'm going to finish this sketch. I'm going to extrude bigger shapes, and I'll go ahead and extrude the whole rectangle just because of design changes. I'm going to change that to a cut, and then I'm going to give it a distance of 1.25. So there we go. We have our flats in there, and again, no matter what design changes we have in the future, if the flats always need to be there centered like that, they will be. So create a new sketch on this, and have another cylinder coming off of this, and it is not concentric. So for this one, what I'd ask them to do is use the tangent constraint, or I'd show them that I can make that tangent to that circle, and then I'm going to use my horizontal constraint. Actually, I think I am rotated 90 degrees out. There we go. So that's really going to be a vertical constraint. So I want the center point of that circle to be constrained vertically to the center point of that one. That'll keep it in line, and then all I need is a diameter dimension, and that is 1 inch. And that circle's done. We're going to finish that. Oh, I picked the wrong circle to be tangent to. Look at that. I should have been tangent to the smaller one there. I wasn't paying attention. Let me undo some of that. Sometimes it's just easier to undo than it is to find that pesky constraint and delete it, although we can. So I need that to be tangent to this. I need my vertical alignment back. And I need my dimension. There we go. Finish that. Extrude that shape. That goes 2 inches. There we go. So now we're starting to get the shape that we wanted. There is a kind of a rectangle cut out here, a keyway, if you will. And I show them a couple of different things. First of all, I show them that we could just use this flat right here as our sketch plane. And even though we're not going to actually sketch on this surface, which is relatively new to them, we can just simply put a rectangle in here. And then we can start to dimension this. The rectangle, let me bring that PDF back. I've been intentionally given them how deep this rectangle or this key should be cut in from the center line of this cylinder. So, yeah, you can do the math and you can figure out how tall that rectangle should be based on the radius of this part. But, oh no, I'm sorry, it's from the top edge. My bad. It is, oh, that the center point of the circle is, or cylinder here is from the center line of this one. That's what I was thinking. Okay, bring that back. So we can do this one primarily through dimensions. Now in this case, when we have a cylinder, I need to grab the edge of that cylinder. And Inventor's not going to find that because that's not an actual change in surface direction. So what I need to do is just simply use my project geometry and ask Inventor to project that edge. And let me orbit around here a little bit, and you can see it's projected that edge up to my sketch plane, and I can dimension it. So go back to my view here, and I can start to dimension this using that projected edge. It should be 0.75. Distance from the edge here, need 0.75 there, and then I have a width, and that is 1/2 inch. And I probably should project the bottom edge of this cylinder, and then use my coincident constraint, and put that point coincident to that, so my rectangle is the appropriate size. Finish that, and extrude that rectangle to cut. And I spend some time talking about how we can specify these distances. So for instance, in this instance, I want that extrusion to always go through the model. So I don't actually have a distance. I want it to go through all. And the reason I tell them that is because if I give it a distance and for some reason the diameter of this cylinder were to change dramatically because of a design revision, your distance may not be enough. So as long as you set the rule up so that we extend all, we know that no matter what size changes happen, we're going to go through the whole thing right here. Now there's some fillets in here, so I would go through this fillet command pretty in depth. I would talk about that we can select edges, loops, we can fillet an entire feature, we can set up the different radiuses. We can do variable fillets where it starts out as one radius and ends as a different radius. That we can set it up as setbacks to specify our distance. We can edge fillet, we can fillet faces, which we don't have any right now. Then we can do a full round fillet. There's some different possibilities down here, so we can roll along sharp edges, roll the ball when possible to keep our fillets nice and fluid, so on and so forth. So on this one, our fillets they're 1/8 of an inch, perfect. So I can just go through and select the edges I want to fillet, which should be these. And I have a couple of chamfers. Same thing, different possibilities for specifying your chamfers. I would cover all that with the students. They are 1/8 of an inch here, so I can just select my chamfered edges, spin this around. Here we go. So we're able to get that done in pretty short order. The other thing I would show them that instead of sketching on this flat surface, I would start the subject of planes, and Inventor does a nice job of breaking the planes up into the different possibilities, where I know some softwares you can just pick on what you want to make a plane, but it's a little hard to communicate to the students what's required for a plane. So here it's kind of broken down that if I want to do a plane, I want to do this one tangent to a surface and parallel to a plane, I know exactly the two things that I need to pick on. I need something to be tangent to, and I need something to be parallel to. And so there I have a plane in there, and I could have done that rectangular cutout on this plane. So 6 of one, half dozen of another. The next one that we're going to do, let me get my PDF up here. I came up with this one specifically for planes, so that they were forced to use planes, and also forced to use an auxiliary view in their detail drawings. We also introduced some GD&T in this one, in so much that they have to duplicate these feature control frames and some of the basic dimensions. So in the detail drawings for this one, and we would be detailing all these out in orthographics. So for this one I wouldn't lead them through the entire thing by any stretch of the imagination. I would just try and give them some pointers and give them some suggestions on how they might accomplish this. So this one kind of had the main body section was an L, and I would give them some different possibilities that instead of drawing all the lines to make up that L, that I could potentially just do 2 rectangles, and I could get my L shape out of those 2 rectangles really rather quickly, so that all I have to do is apply some dimensions here. That should be 1/4 of an inch, and then this should be 1/4 of an inch as well. So as part of the design intent, I would make sure that they are interrelating dimensions and that they're starting to set up equations in their dimensions, so that you communicate the design intent and things. You change one thing, and everything else that needs to change does change on its own. So it tells me that that's dimensions driven by an equation, a very simple equation, but equation nonetheless by the fx on there. So that would be something I would finish that sketch and then extrude that part of it, and that should be 3 inches. So we're ready for a plane. This is going to be a plane at an angle and parallel to an edge, or around an edge, I'm sorry. So I'm going to be parallel to that, and I'm going to go against that edge, and I can kind of see the angle that it's given me there, so I'm going to put in my 45. I got a chance to see that that's not the 45 I wanted, so I'm going to change that to a -45, and that gives me my alternate. And then sketch on that plane. And here's where a lot of people, a lot of students, kind of don't have the idea just yet, not solidly, because they see this as this cylinder has a hole in it, so they're going to create this donut shape. If I didn't warn them, and I usually don't, I let them go ahead and do that, and then they're perplexed why that hole through the center doesn't go all the way through. So that's 1 inch. This one is 3/4 of an inch. Need some placements here. That should be 1.5 inches. That should be 1 inch. So for this 1.5 inches, we can put in that dimension. We can do the math in our head. This was 3 inches across, or I can simply add this dimension, and I would encourage them to do this, is to go in and use the show dimension. I want to show the dimensions for this object. And I want to find that 3 inch. It's right there. So I want that 3 inch dimension. That was my width here. I want to divide that in half. That way, if a design change were to change the width of this part from 3 inches to 2 inches or to 4 inches, that I would be guaranteed this feature would always be centered. So it's driven by an equation. And then I can finish that, extrude that shape, that donut. And this is also a good opportunity to talk about what Inventor calls extents. Different softwares have a slightly different terminology for this. But if I just give it a distance, I'm going to flip the direction that's going. I'm never going to get that the right distance for this donut to stop right at this surface. It's always going to protrude through the bottom, or I'm going to have a gap on the top. So we have other mechanisms for that. So Inventor calls it the to extents. So I get to pick what I want to extend to. And now I have a perfect extension down to that flat surface. But what they're perplexed about is that this circle did not go all the way through. It's still solid in the bottom because there was nothing there cutting. We were only joining at this point. So really the correct, if you had some insight, the correct method would be to just put the outer circle up here, get it up there and get a solid cylinder in, and then come in and do the smaller circle and have it extrude to cut all the way through this. So I'm not going to do that right now. I'm going to get rid of my work plane for just a minute here, turn its visibility off. What we need is some holes next. So in Inventor, what we do is we place points first where we want these holes. And when we talk about holes in these points, I give them a couple of different options. First of all, I can use my horizontal constraint, and looks like my view is turned 90 degrees here, so horizontal is really vertical. There we go. Now we're looking as horizontal being horizontal. So I can set these in here using some constraints, and then my vertical constraint. That way, if I move one, I always have my square pattern, so I try and reinforce that to them. And apply some dimensions to these points now. I'm not going to fully dimension these. I'm sure everybody understands dimensions. I think that's 0.75. So I would dimension my points. Wouldn't need many, just actually 3 more, and I would have my points completely dimensioned there. I'm going to finish that a little early, and I'm going to go into my hole feature. So this is how Inventor does holes. And I can do a simple hole where I just specify the diameter. I can do a counterbore hole, again, where I put in all the information. This is a spot face and a countersink. But I can tell it that these are clearance holes for fasteners. So if I do clearance holes for fasteners here, it's just going to take a second for the database to load. My computer is old and slow in my office, so I get a lot of time to wait usually. Here we go. If I make that a counterboard. And so I show them that you can just simply select the type of fastener you're going to put in, and the diameter of the fastener. We can pick its fit, whether it be a close fit, normal fit, loose fit, which is coming right out of the machinery's handbook. And then all the dimensions for that standard are automatically applied. Termination, I can say through all. So you can see my holes going in here, and actually the one I picked, my counter bores are way too big. They're punching all the way through that surface, but let me pick a little bit smaller one here. There we go. So just a quick way to get those in there, and then there's some fillets and some rounds on this part, but you've already seen that. So with just a little forewarning and a couple of hints, I would expect by the 7th lab here, my students would be able to accomplish that. By the way, the class meets twice a week for 3 hours at a time, and they would probably accomplish 3 labs, 2 to 3 labs, depending on where we're at, if we're at the beginning or the end of these, in 1 3-hour session. So this really goes pretty quick. We don't dedicate much of the semester to these 10 labs. They have to be fairly fast at it. So I thought we'd kind of jump to the last one here. Let me bring that up. Last of the labs that really don't go together in any shape, form, or fashion. This one is an angle plate that had out in the machine shop, and so I just kind of modeled that and came up with the detailed drawing. So this is an actual part. It's a cast part. Has some machine surfaces on it. So in the detailed drawings, I would ask them to actually take a look at the actual part and start applying the surface finishes to the detailed drawings. They're not necessarily given on the part. But what I like about this one is it allows me to use a lot of planes, set up symmetry, and set up mirror features so that I can get a fairly complicated part for where we're at in the curriculum done without a lot of effort. So trying to show them the advantages that the software provides and use those advantages. So since this is an angle bracket, again, I could just draw the L with all the line elements in there, or I could just simply use 2 rectangles to create the shape that I'm looking for. Oh, picked the wrong one there. We'll come down from this corner. Set up some initial distances here. That leg is 3 inches. This leg is 3.9 inches. Then my thickness of my section here should be 0.56. And that's the same for the bottom, so I'm going to use an equation for that. There, I'm fully constrained. Finish that sketch, extrude that shape. The overall is 5.875. There we go. So I have a couple of things going on this part. There's some slot cutouts in here, and the slots are centered in the part. So what I can do is I can put the first one in here, get a new sketch, and I will use my slot tool. Create the first initial slot. Go ahead and dimension that up here a little bit. Well, those are 1.5 inches. Radiuses are 0.25. And then I have some distances here. So this slot is centered left and right. So I could set up an equation for that. I could call up my distance here, or momentarily I would finish my sketch, and really what I would prefer is just to put up a midplane between that surface and that surface. So that defines my center, and no matter how my length of my part changes, my midplane is always going to be in the mid. And at this point, or maybe even before this point, depending on what questions have come up, I would explain to them the order of the tree over here, that sketch number 2 in no shape, form, or fashion can see work plane number 1 here because it's physically listed below. but there's no reason I just can't pick it up and move it, and then come back and edit my sketch. And now I'll need to project that plane onto my, at least I think I will, yep. And I can just set up a coincident constraint between the midpoint there, and now it's always centered. The dimension for this, its placement, is dimensioned about the middle of this, so I was a little premature coming back. I'm going to set up another midplane. I'm going to set it up, it's from this surface to that surface. Again, I'll move that plane up so Sketch 2 can see it, and then I'll go back and edit Sketch 2. And I'm going to project that midplane onto my sketch plane, and then add a dimension in here from here to there. That should be 1 inch. Finish that. Extrude that slot to cut through all. There it is. Now I'll use a pattern feature, so I'll use the mirror pattern, and I'm going to mirror that feature about this plane. So that's in there. I don't have to create another slot. And by the way I've set this up with my midplanes, that no matter how my design changes, I know these two cutouts here are always going to maintain the design intent of being centered left to right, and then being symmetrical about the middle of this surface right here. So that would apply to all the slots on this. There's really quite a few. I'm not going to do all the slots. And then we have some ribs in here. So this gives us the opportunity to talk about an offset plane. So we would talk about that. I'm going to offset that plane for my supporting rib, and it looks like that should be negative 1.25. And so I'm going to do a new sketch on that plane. I'm going to go ahead and I'm going to cut back to that plane, so I've just kind of visually removed my geometry that's sitting in front of that plane. Seems to make them a little bit more comfortable when they can kind of see this has been cut away. And what I really just need in here is just a single line. I don't think I got that coincident, or coincidence. I'm going to make sure that endpoints are on the surfaces I want them to be on. I'm going to set up a quick dimension from the end point of that line to this edge. That should be 0.1. And same dimension here. Didn't get the geometry that I was shooting for there. There, I think I got the end point. Here we go. So I'm going to make this one the same as that one because they're equal. And then I'm going to use the rib tool. Where did my rib tool go? Or no, I'm still in sketch. I'm sorry. I'm going to finish that sketch. Then I'm going to use my rib tool and make a rib out of that. And nope, I need to go the other direction, and that rib should be, what are those ribs? There are 0.375. So I'd put that rib in there, and then use the mirror feature to mirror that rib from that side to the other side, because there's one on the other side that's symmetrical. And then add my fillets and create detailed drawings, add finish marks, things of that nature, and this one would be done. So that's the 10 labs that we start off with. Do you guys have any questions or comments?
No questions. Good stuff. I'm looking at your models, and obviously, you know, these are. I'm wondering how. You mentioned pacing, timing, so I think that yeah, you're probably right up there. Do you get students that that straggle, and you kind of have to get them? How do you just send them home, or how do they do this work outside of class? Do
Well,
they have any way to do that?
Yeah, they can come into the lab outside of class, and we get some students who do that. And since this is an Autodesk product, they all have access to it at home. They can download it from Autodesk. They get the full-blown version, and that guarantees they can use the same version we're using in class, because different versions always offer a little bit of complexity if it's as you're moving back and forth. But
or if they won't load each other.
Right.
That's the problem that we have with Solid Edge. You can't load the later versions into the earlier software.
Right. Yeah, and that's pretty common. And that's because they want everybody to upgrade. So they want to remove all the reasons why you could stay on a later version, because then you aren't buying the new version, or you haven't paid your subscription or what have you. So
exactly.
Yeah, we get some people who just can't see the workflow here in the world of parametrics. So there's always one or two in a class. And what I see the most is that if I have a sketch here, and I'm just going to put up a quick sketch, and for whatever reason they finish that sketch, their first instinct to go back and do more work on this is to do a new sketch. And they'll ask, well, why can't I dimension that circle? And so you have to spend some time trying to get them to see that, you know, that circle is really in sketch number 4, and sketch number 5 doesn't have any relationship to it. The other thing that I see people do, let me get rid of that sketch number 5. We don't need that. Where'd my delete go? No, I'm not seeing it. I'm just going to undo. There we go. Is that, I'll edit that sketch. That when they're starting some of these parts, they'll put way more geometry up there than they need. So, for instance, they'll think, well, while I'm in this sketch, yeah, not only do I need a circle there, but at some point I'm going to need a rectangle over here, and then maybe there's another slot over here somewhere, and I'm not dimensioning any of this. And they'll finish that sketch and they'll say, all right, so I'm going to extrude, and I'm going to extrude that circle. We'll just go ahead and take it as that. They'll go, well, where'd my other geometry go? Just not kind of seeing the workflow here and how the softwares work. So they work against it, they don't work with it. But I try and spend some time individually and try to get them over that and see the things that they're missing. So.
No, that's great.
Yeah. So this should take the 10 labs. If we meet twice a week, it's going to take about 2 weeks to get through those 10 labs. And then we're going to be off in something else. And the AutoCAD class, the first one, I really grade them hard on their dimensioning and their detail drawings and intersections of lines and hidden lines and center lines, and I really hold their feet to the fire. But when it comes to this class, I back way off, because first of all, the detail drawings are always right. You're not going to have any missing hidden lines. Dimensioning, I take some points off, but I relax that a little bit just because I want this to be fun, because this software is fun. People should enjoy it. And then, so I really just look over their drawings for any major dimensioning mistakes, and then, are all the dimensions right? Did they build the model correctly? So, it's real easy for people to get, 100% on all of these labs for the first 10 labs. Not everybody, but
sure.
So part of the rigor comes from the pace, that if you can't keep up with the pace, you may not get lab 10 done, or you may not get lab 9 done. So then the grading kind of works out for this section. Well, you got 9 out of 10, and as long as the
90%.
first 9 look pretty good, you got 90%. So that's kind of how I handle that. I've often thought about I really should be looking at their individual models, having me send their model file so I can kind of take a look at what constraints they used and if they dimensioned everything, but there just really isn't enough time in my day to do that.
Believe me, that's where I'm sitting here thinking, you know, how, like, I open up model files and I go in and I try to dig through them, but it gets really cumbersome to do that.
Yeah.
You know, for 20 students at a time, it's a lot of models
right,
to go through and dissect.
Yep, and
then
so
report what's wrong with each one of them.
Right, and there's so many more productive things you could be doing with your time.
Yes.
I just have them turn in the detailed drawings. I just create a rubric. Do you get all the dimensions in there? Are the dimensions right? Do you have all the features? Do you have all the views I asked for? Check them off, give them a grade, and we move on. So, because I think the real potential for evaluating them is when they're using the software for what it was intended to be used for. So when they're designing things, for when they're doing the reverse engineering, and when they're coming up with their own models to solve a problem. That's what the software is intended with. That's what they're going to use it for when they leave here. And so that's where, you know, I can really start assigning grades and looking at the class in a different way than just how many points can I take off on this and how many points can I take off on that.
Sure.
So, real quick before I leave you here, we would have went through all the toolbars up here at some point during these 10 labs. The inspection toolbar, I want them to be able to look at distances and angles on parts and use that. Would have went into the view ribbon, and I would have different styles and different things of that nature, so I can turn on grounding planes and I can do section views and things of that.
Shane, do you find that you have to walk them through all the buttons for them to go in and access them, or do you leave them to explore a little bit more on their own? I've kind of tried to do the latter, and I'm not sure if that's walking them through more of the buttons seems like it might be a better way to do it.
Yeah, I show them that all these things exist and that they can use them to their advantage. It makes the software, it makes the process easier. Now, do I force them to do section views? No, I don't force them to, but when they call me over and they're having a problem, tell them, look, if you would just use a section view and get rid of part of this part, you could see what you wanted to see. Or if you turned on the grounding plane, you'd have a little bit better visualization on where you're at in this. So I kind of leave it up to them. I dangle the carrot out there. If they grab it, they grab it. If they don't, you know, I don't force them to. So.
Sure.
So
I run a project that basically gives them parts that later on they assemble, where to properly present the parts, they're going to end up having to do auxiliary views, section views, and things like that. They got to bring that all together in a portfolio. So I do grade them as to whether they have their views, but they have a rubric beforehand that says, do you have an auxiliary view, yes or no? But also, the nice thing about Autodesk is it has a great help menu. They have great tutorials. So I will usually demonstrate once or twice and then tell them that reading is fundamental and that they can't be going to their boss all the time asking them how to run the software. They got to figure it out themselves a lot of times. And let it go from there.
Yeah, when Autodesk went to the wiki style help really became helpful. So, and I'll kind of do the same thing that I'll have them, you know, tell them that they can use the help, and if they're asking me a question that I think they should already know the answer to, I tell them, well, you're going to have to go to the help and look it up yourself because I already covered that and evidently it didn't work for you, so you're going to have to try something else.
Another outstanding source for Autodesk help is YouTube.
Yes.
There are tons and tons of YouTube videos that will show them how to do things. In fact, even some of the projects that they do, will be on YouTube video to actually do things, plus a few cool things.
Mm-hmm.
Between the help menu and the tutorials that Autodesk provides and YouTube, if they were motivated, they really could teach themselves everything about this program.
Right. But what I'm always hesitant on is, I mean, I agree with you. I totally agree with you. But I found a little bit that it's the idea of you can get it done, but did you get it done professionally? Did you get it done how I want to say how I wanted you to get it done? But on these first 10 labs, I do have, some very specific requirements because I want them to be comfortable with the constraints, and I want them to know how to build intelligent models that are going to adapt to design changes and things of that nature. But as we move on through the course and we go into assemblies and sheet metal and things of that nature, I absolutely do open it up a lot more to those type of things. The first 10, I'm kind of a stickler on.
Well, I will say YouTube really emphasizes dimensioning more than they emphasize constraints.
Mm-hmm.
When it comes to building objects.
Yep, I don't think everybody just really has that concept.
No, I agree with that.
So
Sure, yeah.
And you don't get it till you have to go back and edit some of the junk that you've created. And, you open that file up and you try and do some simple edits, and now you're in the middle of a hornet's nest and you're going, wow, I almost have to start this part completely over because this was terrible. Or to edit somebody else's work, which is really the norm in industry.
Sure.
One person did not design the Chevy Tahoe or Honda Accord. That's where we're trying to get them. So I thought next time we could do a little bit about assemblies and look at a little bit about sheet metal that we do and a couple of things of that nature. And this is where I was going to end it today, unless you guys have some more questions or comments, or is there something else?
I think that's great, Shane.
Okay. Is there anything specific you want to see that I didn't do or didn't touch on?
No,
I'm very interested. Go ahead, Ted.
Next time, I'd just like to see detail in your assembly as far as your assembly constraints are concerned.
Sure.
And animation that you do and motion.
Okay.
So like the screw that you have currently up on your screen,
Mm-hmm.
do you have them animate that so certain revolutions equate to certain linear motions and stuff?
No, not on this one. This is the first assembly. So
Okay.
I really try and limit what they're doing at different stages in the class. So I just want them to get good at assemblies and exploded assemblies, and there's enough here without having to do all that. Some of the other things that we do, they do a little motion and things of that nature. So we do touch on that. So absolutely. We'll do assemblies next time, and we can cover some of that.
Okay.
All right.
Yeah,
great.
awesome.
All right.
Fantastic.
Thank you very much for joining me today.